Okay, this should be our last video on PGFs, so this is the end of PGFs now. Here we are talking about the sum of independent random variables. So if you have x and y and they are both two independent discrete random variables and they have a PGF of g of xt and g of yt respectively, then if you add the two variables together to give you a new variable z, then the PGF of z is your PGF of x times your PGF of y. Okay, and I'm going to just do a kind of very basic, like made up example to show you why that happens. Okay, so let's just say we've got two dice. We've got dice A and dice B, and I'm going to say that dice A has 3 faces with a 1 on, and it has 3 faces with a 2 on. And then I'm going to say that dice B has 2 faces with a 0 on them and 4 faces with a 1 on. Okay, so if we think about what their individual probability mass functions would be, let's call ax and by, then with x, obviously when I roll this dice I can either get a 1 or a 2, and the probability that I guess a 1 is a half, and the probability I get a 2 is a half. Okay, and then if I call if I call dice by, when I roll dice b, I can either get a 0 or a 1. The probability of me getting a 0 is a third, and the probability of me getting a 1 is 2/3, because it would be 2, 6 and 4, 6. Okay, right. Let's then work out what the probability generating functions for these are. So our probability generating function for x is going to be, don't forget it's how you're doing this, you're doing a probability mass function times t to the power of x. Okay, so here that is going to be a half t to the 1 plus a half t squared. That's going to be our PGF for x, and our PGF for y is going to be a third t to the 0, so that's just a third, plus 2/3 t. Okay, we're going to use those in a second, of course. So we know that to be true. Now let's just then say we had a new variable z, which is our x plus our y. Okay, so it's when we roll both dice and we add the two scores. Okay, so when we roll the two dice, obviously we could get, you can't get 0 because there's no 0 there, so that you could get a 1, so that would be doing a 1 plus 0. You could get a 2, which would be doing 2 plus 0 or 1 plus 1. And you could get a 3 by doing 2 plus the 1. Okay, so if we try and then work out our probability mass function for that, so obviously the to get a 1, you need to go, you need to roll a 1 here, so that's a half, and a 0 here. So it's a half times a third, so that's a 6. If we want z to be 2, you'd have to do a 2 here and a 0 here, or I'm doing this like a tree, if you can see what I'm doing, a half times 2/3 there. Okay, and if you did that, that's going to be a 6 plus 2 6, that's 3 6, so that's a half. And then to get a 3, we'd have to do a 2 here and a 1 there, so that's going to be 2 6, so that's going to be a third. Okay, so that is our probability mass function for z. Okay, which means we can then pull off what our PGF for z is going to be. So our PGF for z is going to be a 6th t to the 1 plus a half t to the 2 plus a third t cubed. Okay. Now I'm saying that, or we're saying in this video, that you can get the probability of that by doing the PGF of x times the PGF of y, and it should give you the same thing. So let's check. So here's our PGF of x, which is a half t squared, and our PGF of y is a third plus 2/3 t. And so if we expand those, we get a 6th t plus a 6th t squared plus a third t squared plus a third t cubed. And if we tidy that, we get a 6th t plus a 6, and then that's 2 6, that's 3 6, that's a half t squared plus a third t cubed, and that is what we got up here. So happy days, it works. Okay, that's me showing you that it works. We're going to do some examples of it now. So our first example is here. We've got a g of x is a half plus a half t, and oh, is that the same as the ones we've just done? No, it's not. It just looks similar. Yeah, they're not the same. They just look similar. So we've got g of x is a half plus a half t, and g of y is a third plus a half t plus a 6t squared. And we've got to find the PGF for z, which is x z, which is x plus y. Okay, so our solution is just going to be that to find if we know that z is x plus y, we just need to do the probability generating function of x times the probability generating function of y. So we've got a half plus a half t. You can just quote this, okay? You don't have to prove it. I mean, I've just shown you it works. Obviously, it just worked for that example, which wasn't a proof. But happy days, you can just prove it, okay? You can just use it, sorry. So when we expand all of this out, we get a 6 plus a quarter t plus a 12t squared plus a 6t plus a quarter t squared plus a 12t cubed. And so that is, if we tidy, a 6 plus a quarter plus a 6 is 5/12 t, and then a quarter plus a 12th is a third t squared, and that's a 12th on its own, t cubed. That is our PGF for z. Okay, right, then it says use PGFs, this is question B, use PGFs to show that E of z is E of x plus E of y. Okay, so we know that E of x is given by the g dash of x of 1. We know that from the previous video. So let's put that into x. So if we take our probability, if we take our probability generating function for x and we differentiate it, g dash x of t is just going to be a half. So then when we put 1 in, obviously that's not affected. So our E of x is just going to be a half. Let's do the same for y. So d dash y of t, if we're differentiating this function, it's going to be, you can't see, can you? It's going to be a half plus 2/6, so a third t. Okay, and then if we put y in, if we put 1 into there, we're going to get a half plus a third, lots of 1, and a half plus a third is going to be 5/6. So what we've got is E of y is 5/6. Okay, and then let's do the same for z. So g dash z of t, we've got to differentiate all of this. So we get 5/12 plus 2/3 t plus 3/12, which is a quarter t squared. Then we can substitute in 1 into there, so we get 5/12 plus 2/3 plus a quarter, and that is 4/3. So E of z is 4/3. Okay. Then, if we think about E of z we're going to suggest is E of x plus E of y. So E of x is a half, E of y is 5/6. So that is 4/3. Which is what we've got for E of z as required. Okay? Right, second example. Our last example is on something slightly different, but not too different. It won't take me very long at all. So there's a discrete random variable x and it has a PGF gx of t. Then the PGF of y, and this y is not the sum of two variables, it's a constant times a variable plus a constant on the end. Now that is like when we do discrete distributions and you times that variable by a constant and you add a constant on the end, okay? If that is true, then what you do is you do t, so your dummy variable, to the power of the thing on the end, the constant on the end, and then you do g, your PGF of t to the power of your constant at the front. Okay, so here we go with our example. So the first one asks us to write down the distribution, the probability distribution of x. So we're going to do that in a little table. Obviously, here is our probability generating function. The coefficient is our probability, and the power is our option, so our x value. So our x value there is 0, our x value there is 1, that is a third. That is our probability mass function, that is our distribution. Okay, right, then we've been given this function, y is 2x plus 1, and we have to write down the PGF. Okay, so we're going to do that by putting it into this this box here. So 2x plus 1 is going to be, which is our y, and then the probability that y equals y. Our probabilities, of course, will stay the same, and our PGF value, our y value is, we're going to substitute these in. So 2 times 0 is 0, plus 1 is 1, 2 times 1 is 2, plus 1 is 3. So that means our probability generating function for y is going to be 2/3 t to the 1 plus 1/3 t cubed. Okay, we've done that just from first principles. Then we've got to verify that this is what it is. Okay, so if we're going to verify it, if we think about g to the y, obviously y is 2x plus 1. So using this formula up here, I'm going to do t to the 1 times g of x of t squared. Okay, that is what I am doing, and I'm verifying that that is true. So that's what I'm trying to prove is true. I've got my probability generating function for y, which is 2/3 t plus 1/3 t cubed. If I take out a factor of t, I'm left with that, and that is just my my probability generating function for x. Therefore, I've verified it's true.